Given a region P in the UV plane, or parametric space, which we transform to a region R in the xy plane, so essentially given a point UV in parametric space, we apply a transformation which transforms every point in P to a point in R. So essentially R is the image of P under the transformation, and P is the pre-image of R. And by a one-to-one transformation means every point in P gets mapped to exactly one point in R. So therefore, we can apply an inverse transformation to get back the point in UV space. So an example of a one-to-one transformation is the expansion in the horizontal direction. So for example, if we have a point in the region P and we apply the following transformation to it, so we have a 2x2 matrix representing the transformation, which has entries of 2, 0, 0 and 1. So the point UV in P gets transformed to a point xy in R. So if we suppose we have a square in the UV plane, so we have the coordinates 0, 0, 1, 0, 0, 1, and 1, 1, and we apply this transformation to every point in this region. So if we evaluate this multiplication, we get x is equal to 2u and y is equal to v. So this point in the UV plane gets transformed to a point with coordinates 0 and 0 in the xy plane. So that doesn't change. And the point 0, 1 gets transformed to the point 0, 1. So that stays the same. And the point 1, 0 gets transformed to the point with coordinates 2 and 0 in the xy plane. So this moves here. And finally the point 1, 1 gets transformed to a point in the xy plane with coordinates 2 and 1. So therefore this square gets stretched into a rectangle. And this is a one-to-one transformation because we can take the inverse and get back to this square. So essentially, UV is equal to the inverse of this transformation matrix multiplied by the point xy. Now an example of a transformation that is not one-to-one is the orthogonal projection onto the horizontal axes. So what we have is xy is equal to the transformation matrix having entries 1, 0, 0 and 0, and we multiply this by UV. So as we can see, this multiplication gives x is equal to u and y is equal to 0. So applying the transformation to this point in the UV plane, it maps at the same point in the xy plane. And similarly, this point in the UV plane maps to the point with the same coordinates in the xy plane. And then applying the transformation to this point, well, this also maps to 0, 0. And applying the transformation to this point in the UV plane, this point maps to another point with coordinates 1 and 0 in the xy plane. So this rectangle gets flattened into a line. And the inverse of this transformation does not exist because this matrix is not invertible. And this occurs when a transformation is not one-to-one, where we see 2 points in the UV plane mapping to the same point in the xy plane. Given our region P in the UV plane, to which we applied a one-to-one transformation to map a point in the UV plane to exactly one point in the xy plane, So we have the region R being the image of P. We saw that our transformation equations are of the form x as a function of the parameters u and v, and y is also a function of u and v. So if we take a small element in the uv plane, which has a width delta u and height delta v, and we look at this corner point having coordinates u0, v0 in the uv plane, then this point gets mapped to a corner point on this element in the xy plane. So this point will have coordinates x0 and y0. Now if we draw a position vector in the xy plane, then this position vector has an x component, which is a function of u and v in the horizontal direction, and a y component, also a function of u and v in the j direction. And if we take the partial derivative of the position vector with respect to u, we get the partial of x with respect to u in the I direction, plus the partial of y with respect to u in the j direction. So we're looking at the change in r as we walk along the u direction. And this bottom edge on this element in the uv plane maps to this bottom curve in the xy plane. So this partial derivative gives the tangent vector to this curve when evaluated at u0 and v0. Noting that the coordinates of this point are x, evaluated at u0 and v0, and y, also evaluated at u0 and v0. Now similarly, if we take the partial of the position vector with respect to v, we get the partial of x with respect to v in the I direction, plus the partial of y with respect to v in the j direction. So essentially, we're walking in a direction v in the uv plane along this edge of the element, so that represents this curve over here. And therefore this partial derivative gives the following tangent vector to the curve when evaluated at u0 and v0. So essentially, if we multiply this tangent vector, being the partial of r with respect to u, by an increment u, so that means we walk an increment u along the tangent vector, and for the other tangent vector, we multiply it by an increment of delta v. So as we walk a distance of delta v along this edge in the uv plane, then we walk at some distance along this vector in the xy plane. So essentially we're just multiplying the vectors, each by a scalar. So these tangent vectors look something like this, for example. So these essentially form a parallelogram. So what we do is take the cross product between these two vectors. So we have the I, j, and k components. And for the first tangent vector, we have the partial of x with respect to u by delta u, and the partial of y with respect to u by delta u, with a 0z component. And we have the partial of x with respect to v by delta v, and the partial of y with respect to v by delta v, and a 0z component. So what we get is the partial of x with respect to u by the partial of y with respect to v by delta u delta v, and minus the partial of y with respect to u by the partial of x with respect to v by delta u delta v. So this is essentially the z component of the resulting vector that points out of the plane. So factoring out delta u and delta v, we have the partial of x with respect to u, by the partial of y with respect to v, minus the partial of y with respect to u, by the partial of x with respect to v. And that's multiplied by delta u, delta v. So let's just make a bit of space here. So we have delta u, delta v. And this quantity here is the Jacobian of the coordinate transformation of x of u and v and y of u and v. And this entire expression, being the cross product between these two vectors, gives an approximation to our area element in the xy plane. And now let's make a bit of space here. So in the limit, as delta u and delta v tends to 0, then the area tends to 0, and we obtain the following expression for our differential element, being the Jacobian of our transformation from the uv plane to the xy plane, multiplied by du dv. So given a continuous function f of x and y, integrated over region R, which we can use an iterated integral to integrate with respect to x and y, that's equal to the double integral of our function of x, which is a function of the parameters u and v, and y, being also a function of u and v, multiplied by the absolute value of the Jacobian of the transformation, integrated over the area of region P. So with respect to u and v. So essentially we can evaluate this simpler integral over the region in a uv plane, rather than evaluate a more complicated integral over the region in the xy plane by using a coordinate transformation. So this can only be done if the transformation from uv space to the xy plane is 1-to-1. And noting the Jacobian can be written in determinant form to make it easier to remember. So we take the partial of x with respect to u and v in the first row, and the partial of y with respect to u and v in the second row. And we'll look at some examples to make this clear. For the polar coordinate transformation given by these two equations, find the Jacobian, sketch the regions in the r theta plane and xy plane for r between 0 and 1 and theta between 0 and pi, and write the Cartesian double integral as a polar integral. We'll recall that the Jacobian for the transformation is equal to the determinant of the partial of x with respect to r and the partial of x with respect to theta and the partial of y with respect to r and the partial of y with respect to theta. So the partial of x with respect to r is cosine theta, and with respect to theta is minus r sine theta. And the partial of y with respect to r is sine theta, and with respect to theta is r cosine theta. So evaluating this determinant, we get cosine theta by r cosine theta, which is r cosine squared theta, and we have minus r sine theta by sine theta, which is plus r sine squared theta. So the Jacobian of the transformation is r. And now sketching the region in the r theta plane we have r from 0 to 1, and theta between 0 and pi. So that's our rectangle in the r theta plane. So the boundary line, r equals 1, maps to x is equal to cosine theta, and y is equal to sine theta. So if you square these equations and add them together, we get x squared plus y squared is equal to 1. So from 0 to pi, this is a semicircle with a radius of 1, which looks something like this. And this boundary line, where theta is constant at pi, gives x is equal to minus r, and y is equal to 0. So for r equals 1, which represents this semicircle, x is equal to minus r, and y is equal to 0, which represents this far point over here, where theta is equal to pi. And similarly for this boundary line, we have theta is equal to 0, so x is equal to r, and y is equal to 0. So for r is equal to 1, x is equal to 1, and y is equal to 0. So we get this point at theta is equal to 0. Now suppose we had a line in this region at r is equal to a half, for example. So what we'd get is x is equal to a half cosine theta, and y is equal to a half sine theta. So again, squaring these equations and adding them together, our semicircle at radius 1/2 looks like this. And if we had a horizontal line in this region, for example, somewhere here, at theta is equal to pi on 4, then we get x is r on root 2, and y is equal to r on root 2. So therefore y is equal to x. And that represents this line over here, where theta is pi on 4. And similarly, you can have theta is equal to pi on 6, theta is equal to pi on 2, and so on. So for example, this line would be for theta is equal to pi on 6, and this line in the middle can be pi on 2. So this rectangle, for example, between r is equal to a half and r is equal to 1, and theta is equal to pi on 6 and pi on 4, so this rectangle over here, maps to this polar wedge over here. So we can write the Cartesian double integral over the region R, being this region, of our function of the Cartesian coordinates x and y over x and y as the double integral over the Cartesian region P, and our substitutions would be the function of the polar coordinates. So we have the function of r cosine theta and r sine theta by the absolute value of the Jacobian, which is r, by dr d theta. So this is the exact same result that we got when we found the area of the polar region using geometry. And here, this integral represents the integral of the function by r over the Cartesian r theta plane versus the integral over the region that we had already in the polar coordinate plane. So that's the difference between the two derivations, and they get the same result. Let's evaluate the integral by applying the given transformation. So from the limits of integration, we can draw our region in the xy plane. So we're integrating from x equals y to x equals y plus 3. So the first boundary line is the line y equals x, And the other boundary line is y equals x minus 3. So we have a y-intercept of negative 3 and the same slope as the other line. And then we're integrating from y equals 0 to y equals 3. So our parallelogram is the region of integration. So from this, we can draw our region in the UV plane using this transformation. So when x equals 0 and y equals 0, u equals 0 and v equals 0. So that's our first point. And at this point, x equals 3 and y equals 0. So u equals 1 and v equals 0. So that's our next point in the region. And at this point, using the relationship y equals x, we have x equals 3 and y equals 3. So that gives u equals 0 and v equals 3. And at this point, using this relationship, when y is equal to 3, x is equal to 6. So that's the other corner point of our region in the xy plane. So what we have is u equals 1 and v equals 3. So this is our region of integration in the UV plane. And from this relationship, we can obtain a Jacobian for our transformation, which you can also do geometrically. So the area of this parallelogram is the base by the height, which is 9. And that's 3 times as large as our region in the UV plane. So we expect the Jacobian to be 3. But let's use these relationships. So we have y is equal to v. So if we substitute into this equation, we get x is equal to 3u plus v. And the Jacobian is obtained by writing it in determinant form. So the first entry is the partial of x with respect to u. And then we have the partial of x with respect to v. And then the partial of y with respect to u. And the partial of y with respect to v. So this determinant gives 3, being the Jacobian of this transformation. And now we can rewrite the integral in a simpler form. So we have the double integral, and we have the integral of our function. So doing the appropriate substitution, we have y is equal to v, and x minus y on 3 is equal to u. And that's multiplied by the Jacobian by du dv. So we're integrating from u equals 0 to 1 and v equals 0 to 3. So what we get is 3v e to the u evaluated at u equals 0 and 1. So that gives 3v by e to the 1 minus e to the 0. And then we integrate this over v from v equals 0 to v equals 3. So what we get is 3 by e minus 1 by v squared on 2 evaluated at v equals 0 and 3. So that gives 3 by 9, which is 27, on 2 by e minus 1. Let's evaluate this integral by choosing the appropriate transformation. So using the integrand, we're going to let u equal x plus y and v equal y minus 2x. And using the limits of integration, we can draw the region in the xy plane. So we first integrate over y. So we're integrating between the line at y equals 0 and the line 1 minus x. And then we're integrating from x equals 0 to x equals 1. So that's our region of integration. And now if we subtract the two equations, we get u minus v is equal to 3x on the right hand side. So that gives x is u on 3 minus v on 3. And if we multiply the first equation by 2 and add the equations together, we get 2u plus v is equal to 3y. So therefore y is 2 on 3u plus v on 3. So using these equations, we can draw our region in a UV plane. So starting with this line at y equals 0, from this equation we get v is minus 2u. So that gives a line that has a slope of negative 2. And when x equals 0, we have another equation of v is equal to u. So that's our second line with a positive slope. And we can write the equation of this boundary line as x plus y is equal to 1. So we have 1/3 plus 2/3 gives u. And minus v on 3 plus v on 3 is 0. And that's equal to 1. So our third boundary line is at u is equal to 1. So therefore this point is at u equals 1 and v equals 1, according to this equation. And this point here, according to this equation, is at u equals 1 and v equals minus 2. And now we'll calculate the Jacobian. So the Jacobian is the determinant of the partial of x with respect to u. And we have the partial of x with respect to v. And the partial of y with respect to u. And the partial of y with respect to v. So we have 1/3 by 1/3, which is a 9th, minus 1/3 by 2/3, which is 2 on 9. So the Jacobian is equal to 1/3. So you can verify the area of this triangle is 1/3 the area of this triangle. And what we'll do is integrate over v first, so we don't need to evaluate the integral piecewise. So we have the double integral of our function where we make the substitution u and v. So we have u to the half by v squared multiplied by the Jacobian, and we integrate over v first. So from v equals minus 2u to v equals u, and then over u from u equals 0 to 1. So evaluating the inner integral, we have u to the half by v cubed on 3, evaluated at minus 2u and u. So that gives u to the half by u cubed on 3 minus 8u cubed on 3. So we can simplify this to u to the half by 9u cubed on 3. So that gives 3u to the 7 on 2. And then we integrate this from u equals 0 to 1 and multiply by the Jacobian. So if we take the 3 outside the integral, we cancel this out. And then integrating u to the 7 on 2 gives u to the 9 on 2 on 9 on 2. Evaluated at u equals 0 and 1, which is equal to 2 on 9.